Okay, hello everyone. Despite the profile you see, my name is Patrick Gurney. I am an AmeriCorps member with Conservation Nebraska's Common Ground program. Conservation Nebraska's mission is to protect our state's natural legacy by educating the public, supporting communities, and increasing civic engagement. The Common Ground program educates Nebraskans across the state about conservation issues facing their community and provides them with the tools they need to improve their local environment. We do this through locally led education efforts such as webinars, workshops, and film screenings, and community engagement such as park cleanups, letter writing, and outreach events to address local conservation concerns. There are a few housekeeping procedures to go over before we begin. Please be aware that by default, all audience members will have their cameras off and their microphones muted. Please enter any questions you have into the Q&A section on Zoom, and we will go over all of the questions either during or after the presentation. And afterwards, we will also have a very brief survey that shouldn't take longer than 2 minutes to complete, which we will launch following the presentation as well. All right, please welcome our speaker today.
Hello, thank you for joining us today. Conservation Nebraska asked me to come and speak about solar. My name is John Hay. I'm an extension educator for the University of Nebraska. I teach the public about energy issues. I've been doing that for 18 years. Over the years, those issues have changed, and I've taught about a number of different topics. And obviously, one of the interesting topics in recent years with energy are the renewables. And I know if you're reading the paper in Nebraska that one of the major issues that's being talked about are large-scale renewables. Today's presentation is going to focus primarily on behind the meter because that's what I was asked to talk about. So we're going to talk about smaller systems at homes, farms, and businesses types. But the reality is the systems themselves are similar, and the components are similar, but then obviously the application is a little different, and then the economics and how those play out in reality are a little different. So I welcome you to, if you have questions about large scale, you can ask them, and that's okay, but I'm going to focus more on the small scale today. Also, if you have questions about large scale solar and want to talk more, you'll see my contact information at the end. I'd be happy to visit with you. I do give some presentations on those topics as well, and have reviewed a number of the research papers that are out there with respect to those. So let's just get started talking about how solar works, a little bit of form and function, and then get into the behind the meter part and how that plays out in economics. We're going to talk a little bit about placement of solar panels, and then finish up with some economics, and then talk about things like payback. I installed a system, kind of my introduction to myself. I installed my own system at my home in 2017. I did this as a project on my own because I could do the electrical work on my own home based in my jurisdiction. And then I had a fair amount of experience working with other installers to be able to gain some of this experience. This is the crew that I joke that I hired this crew. These are my kids that were wanting to help with the hole digging. Just flip through these slides a little bit as this thing went together. And here's the solar part, the feet, the racking, the panels, the inverter is a string inverter, which is a little different design than might be happening today because of changes in the electric code. Mine was installed under the 2014 electric code. Here's the disconnect, and then now the inverter's fully wired up and functioning. I did have all of the electric code compliant placards eventually put on before it was turned on officially. It has performed very close to as expected. This is 2024, the last year I have data. And this is the whole year by month. And you can see some months it generated more than I expected, and other months not as much as I expected. And so, you know, a month just to point out could be January. What happens in the wintertime for particularly systems that don't move? The snow gets on them, it gets cold, and then you lose a few weeks. And so January of 24, a year ago, I lost a few weeks of production to some snow and cold weather. Well, December last month was pretty open and actually did better than expected. So across the year, about normal. We are really particularly talking about these distributed behind-the-meter systems today, that like the ones you might imagine on the right-hand side of the screen here. So it exists behind the customer's meter. So essentially, electricity that's generated from the solar gets used first by the residents or the business, and then if there's excess, it might flow out to the grid, and then we have the policies that regulate that. Utility scale solar exists on the utility side. And again, larger scale has some of the same components, just in larger numbers, and gets sold onto the grid and gets used, again, because it's electricity, by the closest user, but gets sold a lot of times on paper to whoever ended up buying that electricity. There's lots of reasons to install solar. One of the main ones is the desire for green energy. And so what we're looking at is the life cycle emissions of different energy systems. And again, this doesn't say small scale solar, it's utility scale, but gives us a sense of where these things play out. We can imagine that coal has high emissions because we're burning carbon. So it has nearly 1,000 grams of CO2 emissions. CO2 equivalent emissions per kilowatt hour generated. Natural gas is lower. Combined cycle natural gas, which is much more efficient, is lower yet. Nebraska's mix, remember, is a mix of all of it. So it's not all coal or it's not all renewables. It's a mix. In 2017, this was their number. And then we have solar 6 to 14. Now you notice that's not zero. I think that's an important consideration, that it's not zero, because it did take fossil fuels to build the panels, to deliver the panels, to install the panels. And so we had some level of emissions, but they're very, very low. And so there really isn't necessarily a thing that is zero emissions. You can see nuclear is 4, wind is 4 to 9. So they're not zero, but they're very low. We can call solar and wind zero. The same reason we can call an electric car zero is if we draw a circle around it, the individual component isn't giving off any emissions at the time it's functioning, but in the life cycle, there were some emissions. And so this is looking at the whole life cycle. So we can get a pretty good sense that they are clean. This is my process for installing solar, and we don't have to read through the whole process. Just know that there's, at the start of the process, the customer is more involved. Then the installer does a lot of the work, and then the customer's involved in the long-term operation and monitoring of that system. Really, what we're interested in today is usually the first steps, which I would suggest the first steps are do your homework. Get your electric rate schedule from your utility and understand it. Write down your goals. Write down why you want solar if you want it. That's going to be important to talk to the installer about. Look at the energy efficiency in your home. Spending dollars on energy efficiency is probably the first thing you want to do before spending dollars on solar. So get those energy efficiency things in place so you're using less electricity. Make sure that this is clear with your homeowners association. Consider what your budget is. Kind of these are the things to get in line before you're ready to call that first installer and talk to them. So these are some of the things you can work on over time. Let's talk about how solar works. How does this solar panel make electricity from sunlight? And so let's get a few component parts here. So when we think about the whole array, the whole solar system, we're going to call that a solar photovoltaic array. It's more than one solar panel. Each solar panel is called a module. And so the term panel and module are kind of interchangeable in society. So don't worry about calling it a panel, but when you're going to buy it online, it's going to be a module because that's what the industry calls it. Most of the solar used today are silicon based, and so that's what I'm going to talk about from how they work. And so in the upper right-hand corner, what I have is a Bohr model of a silicon atom. And silicon has properties that allow this photovoltaic effect to happen. So let's send in a photon of light. And think about a photon of light as a little packet of energy flying in there, and it is going to contact a valence electron, or the outermost electron in that shell, and that electron is excited to a higher orbital, and then that electron is energized. What's going to happen to it is likely just going to fall back, to some state, giving off heat. And that's what's going to happen in a silicon crystal normally. These photons are coming in, exciting the electrons, they're running around, but then they just turn into heat. So the scientists figured out this property, and then they started to capture some of that by attracting it to a electric field. So that now that electron is going where the scientists want. So they put an electric field in. Then the scientists tried to figure out how to put a permanent electric field in. Once that permanent electric field was there, then they could attract that electron to where they want it. To make a permanent electric field within the solar panel, they used impurities of atoms that had more valence electrons, causing a negative general area, and fewer valence electrons, leaving a kind of a generalized positive area. So now you have this negative and positive sides. So they put in phosphorus and they put in boron into the silicon crystal, causing a difference in the electric field. So you have a net negative region and a net positive region. And then those attractions pull on each other and cause a junction in the middle that is then positively and negatively charged on one side or the other. So we have a PN junction in our solar cell that's just naturally there by what it's made of. The scientists then just put in little wires. Let's catch that electron, and moving electrons are electricity. So now we're going to put in our metallic wire. Now let's send in a photon and see what happens. We send in the photon, the electron gets excited, travels to the positive side, travels through the wire. It gives up its excitement to the load, in this case, the light, and then the electron flows to the bottom of the panel and refills. So the electrons are never gotten lost in this process. They just simply get excited, and then their excitement is used, and they go to the bottom. Now, something else is happening that's interesting if you are interested in electricity. And so in this case, I sent the photon in, the electron moved to the top side, but something else moved to the bottom. So let's look at it again. This little red thing moved to the bottom and moved around counterclockwise. Well, that little red thing is actually the hole that is left behind when the electron left. So it's an electron hole, a lack of an electron. And we think about that lack of an electron being like a positive charge. And so that hole, in this case, is actually what we would describe as the electric current. So electricity is moving electrons, but they're moving in the opposite direction of what we were thinking of. What we call electricity is the holes left behind by the electrons leaving, and the holes, that electric potential seeking out the electrons going counterclockwise in this way. So if we were going to label this circuit, the counterclockwise direction would be the positive side, and the clockwise direction would be the negative side. So just an interesting thing. The reason that we do this is because Ben Franklin said so. I know that's a weird way to think about science, but what we had was a scientist that made some observations, and then those observations have stuck, and thus we call the holes the electricity, because Ben Franklin made some observations that led to us labeling things that way. There are generally three types of crystalline silicon solar panels that are out there on the market today. Two of which are really the most common, and that's the two on the left, the monocrystalline and the polycrystalline. Polycrystalline is just what it says. They've taken molten silicon and they have let it cool, and when it cools, it forms crystals in a random, kind of a random matrix, and they're all different angles. And then they shave off little thin layers of it to make the solar panels, and that is polycrystalline. Monocrystalline, they grow giant crystals that are great big. They shave them off so they have very uniform crystal matrix inside, and they're one single color, and they're more efficient. They're also more expensive. And the reality is polycrystalline and monocrystalline last a long time, 25 to 30 years. They're a lot of times warranted for 25 years, but you do gain a little efficiency with monocrystalline, but you're also going to gain a little cost. And so, what I would look at is things like cost per watt, rather than really paying attention to whether it's monocrystalline or polycrystalline. Both are good. The thin film is a little less efficiency. There's fewer of those out there. And so I'm not really going to get into the details of it because it's not real common. But this thin film, they're almost printing those silicon molecules onto a surface, and then they can make panels out of that. So flexible solar panels would be made in that way. They're less efficient. They don't have as long a life, so we aren't really seeing those in the marketplace as much. There are other types of chemistries out there that are becoming more interesting. There may be some in the future that are interesting because they're lower in cost. But cadmium telluride is probably the other one that is the second most common behind silicon. Silicon is by far the most common, but amorphous silicon and copper indium gallium selenide is another that are out there in the marketplace. Solar panels are not the only piece you need. We need solar panels, but we also have to have a way to mount them. And then we have to have a way to connect them together to make our circuits. And then we might have to combine those together, those circuits together in parallel and series, depending on how we're wiring that. We do have to, if it's a ground mount, we have to think about the electric code and covers and things like that. We may have to trench some of that wire, especially if it's a ground mount system. Every system has to have inverters. Inverters take the direct current electricity from the solar and turn it into alternating current grid quality electricity. And so that inverter is really the other big piece. So the modules and the inverter are the two biggest pieces, but then there's all these other pieces that make it function. The disconnect is required by most utilities. You're going to need a different meter that your utility is going to put in. You have to have all the placards. And then we have to do a good job with grounding in both systems, but grounding is going to be a more arduous process in a ground mount just because it's a little more, there's a little more to it in a ground mount than with a roof mount system. So generally, this is what we're looking at, is that our system, solar is creating direct current electricity. That's not usable by our homes or our electric grid. So the inverter has to do its job and make that into AC. And to do that, it has to see the grid, because it has to match. It's, this grid has got a sine wave alternating current, and the inverter has to see that alternating current to be able to match it. So we have to have the grid functioning for our solar to function. And that's the main reason, that and some safety issues is the main reason, like when the grid is down, a solar array, in most instances, the inverter is going to go down and there is no backup power during the time of an outage. It's out just like everybody else, because it needs to see that grid to make that grid quality electricity. There are some ways to get a little backup, but some of those get complicated and some of them get expensive. So generally, solar panels do not generate electricity during an outage. Let's quick follow the direction of this electricity really quick so we understand it. If the grid is functioning and the home is using electricity, we are using electricity from the grid. If it's at night, the solar comes on and the electricity tries to go to the house first, and it does go to the house and gets used. And if there is more electricity than the house needs, it goes out to the grid. And those three transforms are kind of happening instantaneously, depending on what moment it is and what's going on. So we're going to call this grid electricity. I call this grid electricity. I call this instantaneously used solar electricity. And then I call this excess generation, just so we get some terms, excess generation. Let's talk about inverters just for a moment. I'm just going to touch on these really quick. There's 3 types of inverters that can be used, and there's pros and cons to each. But there's different reasons to use different ones. String inverters is one big inverter for the whole system. These tend to be used for ground mounts, not as much for roof mounts. Because of the electric code, 2 things are going to happen. One, if the power goes out and the inverter turns off, these lines here are still energized. And those lines might be running down the side of the house. And so we have energized lines running down the side of a house during a power outage or during a fire event or something like that. So the new electric code after starting in 2017 said you have to be able to shut off all the way up at the solar panel level. And so this can be done with string inverters with additional equipment, but on its own, it doesn't. And that's where string inverters are used for ground mounts more often than for roof mounts currently. The other thing with string inverters is because all of these solar panels are strung together, if I have partial shading, so I have shading of, let's say, these 2 solar panels, I'm likely going to lose the entire string from a production standpoint, or most of that entire string. And so they don't deal well with partial shading. So again, in those most urban environments, string inverters aren't always the best choice. Microinverters are a little different beast because now we do a single inverter under each solar panel, and a couple things happen. One, if the power is out, it'll shut off all the way up here automatically. The second thing that'll happen is if I shade just a little bit of the solar array, I only lose a little bit of the solar array. So better for those partial shading situations. Microinverters are really easy to install. They are a little bit more expensive, and thus, that's why they're not necessarily used when there's like a ground mount with no shade. But when we're doing an urban environment on a roof, microinverters work really well, and they're probably the best choice in most cases for roof-mounted systems. There is a kind of a intermediate, almost call it a hybrid. There's only one. There are a couple companies, but one primary company that sells this, but it's a string inverter with optimizers. In this case, they still have a big string inverter, but then they have DC to DC optimizers that act a little bit like those microinverters, doing some optimization up at that level, but they can also shut it down up at that level. And then they can also, if there was some shading, let's say of this solar panel, we can bypass the electricity. So we're only losing that one solar panel. So that works really pretty well for roof mounted as well. And there are a few of those installed around the Nebraska area. Let's talk about production just a little bit. I'm going to start with the 3 different kind of methods of installation of solar. One is fixed tilt. And fixed tilt could be a ground mount, but it also could be on a roof where it is not moving. It's sitting in place all the time. And what moves is the earth, which then makes the sun go across the sky. And so that solar panel is in its place. There's a really beauty to this system, and that is that there's no moving parts. So very low maintenance. Here's an example of one as a ground mount. You'd imagine this also being a little smaller on a roof. It'd be similar. But this is a ground mount fixed tilt system that doesn't move, tilted at an optimum tilt angle for the region. This again has a string inverter on the back. I'm going to get through these different types of solar, and then I'm going to look up, and I see some questions in the chat. Maybe I'll touch on those before I get any further. So we can do it. This is a roof-mounted system. Again, a fixed tilt roof-mounted system. This one has some microinverters underneath. The second type is called one-axis tracking, and it's one axis because it's only tilting on that one axis. And so that system is on a pole and faces east in the morning And then as the sun passes across the sky, it follows the sun across the sky and faces west in the evening. And then at night, it resets itself back for the morning. This is a picture. This is the most common system for utility scale solar. So although we're talking about residential, I wanted to introduce this type of system just in case so you knew what it was. This is a single axis tracker. And this is actually the solar array that's west of Lincoln, but it is indicative of all large utility solar arrays. So if you're thinking about large ones, this is what it's going to look like and what it's going to do. Two-axis trackers are much less common, but essentially they tilt in 2 dimensions, and they just essentially follow the sun across the sky wherever it is. So if it's high in the sky, low in the sky, it's just facing that sun all the time. Here's an example of one of these in Lincoln that just faces the sun wherever the sun is. Okay, I think I have some pictures. So let's do this and then we'll go back for a second. In this case, the fixed tilt I set at 100%. So this is those 3 solar arrays in all the same size in one location on one day. It's modeled. And so in this case, the fixed tilt, I just said it was 100% just for a number. And then that one axis tracker gets 12%, makes 12% more on that given day. And the 2-axis tracker made 38% more. So it does make a lot of sense that if I do tracking, I'm going to gain more production. But the reality is for small scale systems, that extra maintenance is actually kind of a real frustration. So I would still recommend on small systems, we stick with fixed tilt. And as we get bigger, we go to these tracking systems, and that 1-axis tracker, because it's kind of a sweet spot between more production and lower maintenance than the 2-axis tracker, that's been what's kind of adopted by the industry for large scale. Okay, let's go back here and answer a couple questions for a second here. Scroll up and see them. What if the electricity you produce is out of phase with the local electric provider? How can these systems coexist? Well, the answer is they can't. It has to be in phase with the local provider. If there are some situations where you can disconnect from the utility and create your own AC, and then it doesn't matter if it's in phase because it's not connected. You're disconnected from the grid. But if you are connected to the grid, that inverter has been tested by to prove that it can do what it says it can do, which is generate electricity from the DC into in-phase AC to make it compatible. So it's really important that we use what we would call UL-listed equipment that has been tested for its functionality. So we need to use good equipment for that. And the utility is going to require that. The utility is going to ask you to tell them what inverter you are using, because they need to know that that's going to be a compatible system with their system. You lost generation from snow coverage. Snow melts quickly off my panels. And that is true. If you have a little higher tilt, the snow will melt pretty quickly. I have a 20-degree tilt, which is not a large tilt angle. And then, of course, it's not just snow, but snow in very cold temperatures. So that last January was very cold. And then the snow melts a little slower. Generally, with people with a ground mount and a little higher tilt angle, the snow will melt off in a matter of a day or two. And also a ground mount, you have a little bit of an opportunity if you want to go and clean them off. If it's on a roof, I would say do not clean them off ever, because we do not need you to be on a ladder in the wintertime when it's cold and slippery out there. Just wait for it to melt. But yes, they do melt off reasonably quickly. What about solar systems that are isolated from the grid and not tied to the grid in any way? Okay, so that would be a system that we would call off-grid, and would typically require a set of batteries or a backup generator, because what a lot of times in electricity, we want that electricity to be available to us all the time. And so in this case, we would have this system separated from the grid. And that is possible and legal, but at the same time, it hasn't been very cost effective. It's very expensive to generate your own electricity, especially when it comes to using batteries. Batteries are very expensive. They've come down in price a lot, but they're still very expensive. And so it tends to be a very expensive way to do it. So not very many people. There are a few, but not very many. And in that case, I wouldn't necessarily have to worry about, I still want good UL listed equipment that made a good sine wave for my AC system, but it would be called a grid forming inverter, an inverter that makes its own grid, because we are not connected to the electric grid. And Vern says, I'm referring to a car charging system. So in this case, we can, there are some solar panels out there that we can make. I still might call it off grid, but we could say mini off grid. So we'd say, I'm going to have this little system that has a solar panel and a charge controller, and I plug it into my my car or my RV, and it keeps the batteries charged up so that they're in good condition. And so in that case, I'd have a solar panel and then the appropriate size charge controller. And so that charge controller is making sure, so the solar panel might be making 25 volts, but we need to charge that battery at 14 volts. So it's converting that voltage to the appropriate voltage. It's also monitoring the batteries so it doesn't overcharge the batteries. And so there's two types of charge controllers. There's maximum power point tracking charge controllers and pulse width modulation charge controllers. Maximum power point tracking is quite a bit better, but it's more expensive. So depending on what you're trying to do, I actually have a couple systems that I run a security light out by my chickens, the solar panel, charge controller, little battery in a battery box, and a couple of motion sensor lights. And that's my system to turn on lights when I go out and check the chickens. I'm not connected to the grid, but works fine. You know, not super cheap to put in, but I didn't have to wire a new circuit and try to do that. So I just use this little battery system. If you want to talk about design of those, you could contact me more. Also, there's some other people around Nebraska and Lincoln that can do some of that help. All right, let's talk about the tilt angle just a little bit. Good questions. When we think about tilt angle, 0 degrees is perfectly flat. 35 degrees is like the tilt from the ground, and then 90 is straight up. So there's kind of 3 different angles. So everybody's interested in what is the optimum angle for a solar array. And so in this case, let's introduce azimuth really quick. Azimuth is the direction it faces let's say on a map. So 0 degrees if it faces north, 90 if it faces east, 180 if it faces south. So we would have this tilt angle and the azimuth. And my next slide is going to introduce how the tilt angle and the azimuth on fixed tilt systems impact production. So in this case, what I've got is I took a solar array and I modeled it in every orientation I could in 10-degree increments for azimuth and 4-degree increments for tilt. And then I took the highest production value and made it 100. And so in Lincoln, Nebraska, 100 is a 38-degree tilt angle facing due south. That was actually 100. The other hundreds are just a rounding error from the power or the Excel file, but they're very close to 100. So if we're going to put in a system, really we'd like to put it in facing due south at about a 38-degree tilt angle. But not everybody's house is at an 80-degree tilt or a 38-degree tilt angle. So this is where we can also look and say, well, should I change the tilt angle of my solar panels? Well, my house already faces south, and I have a 412 pitch roof. That's about 95% production of ideal. And so I would say, no, don't change the tilt angle. Just accept that you have about 5% less than if it was ideal. It's still pretty good, and you didn't have to spend the extra money for any extra tilting or something like that. If you do a ground mount, Then we want to get closer to that optimum tilt angle and azimuth. Then we can say, well, what about if I put this on my roof facing east or west? Well, if it's a roof angle, a lot of 412 pitch is a common roof angle, and I go down and face that east, I just lost about 20% production. Same as if I went west, I lost about 20% production. And so that's where it gets a little, putting it on the east or west side is not a deal breaker per se, but it's going to change the economics because your production is going to go down. And that's for a fixed tilt system. Is an annual production. So I have 20% less production annually on that fixed tilt system. We talked about this already, but just to reiterate, that one axis tracker does better because it faces east and west, east in the morning. It gets a lot of kind of that morning shoulder production and then kind of that afternoon production. And one of the reasons that also can be important is that when is our peak energy use and our peak prices. Our peak prices tend to happen in the afternoon in the summer. And so when we can get some electricity during that time, some of that might have actually a little higher value as well. So those larger scale systems like that one axis tracker to get that production during the time that they want it, as well as to get a little more production overall. This is just some sunlight numbers across the United States. And I think what's kind of interesting about this is you might think, well, if I put a solar array in, let's say, western Nebraska, it's going to do better than a solar array in Indiana. Well, that's true. It's going to actually do a fair amount better. But the price of electricity in Nebraska is lower than the price of electricity in Indiana. So the one in Indiana might actually have a better payback because although it made less electricity, the electricity was worth more to the consumer. So it is kind of like yield versus price of corn. You know, we get better yield, but they have better prices. And so, and then in this case, the prices are enough higher that they do better. Not to say that Nebraska is bad. I'm just suggesting that the sunlight is relative, and the price of electricity is the other factor that's really important. Let's talk about the economics a little bit. But the price of solar has come down dramatically. And so really we're seeing prices, for residential systems over $7 a watt back in 2010. And now residential systems are coming in really under $3 a watt pretty regularly. So it's amazing how far they've come down. Now they've gone down and come up just a little bit. Some of that has to do with a lot of other factors, including inflation and other things, but they are pretty far down. If we were to look at commercial systems today, commercial systems exist down here in the $1 range, $1 per watt installed. I say commercial utility scale systems. There's because they put in so many panels, there's economies of scale, and they actually are much lower cost than these. These residential and commercial are kind of like a house and a business size, and then there's the utility size that's actually quite a lot bigger. So when we think about this system, we're going to pay for the system. And so when we talk about dollars to buy these, a lot of times we like to put them in dollars per watt. So if I had a 10,000 watt system, a 10 kW system, and it cost $25,000, it would be $2.5 per watt. The beauty of doing it that way is that I can kind of compare systems, because I might have one quote from a person that said, well, we think 10 kW will fit well on your house, and another that says, well, we think it's 8 kW. Well, they're different prices, but what is their price per watt? Now I can compare those two prices. And so take things down to price per watt, and look at it that way. It really helps compare systems that are different sizes. So you're going to pay a price per watt. So let's just use that example I said. Let's say this is a 10 kW system. That's 10,000 watts. At $2.5 per watt, that's $25,000 for that system. And that's the check you're going to write. And that's an important factor too. Don't think that the tax credits and things come off of that yet. They don't come off of it originally. You have to pay the full amount. Then when you do your taxes, you apply for your 30% tax credit and get that off. If you live in Lincoln or Omaha, maybe you apply for their incentive and get their incentive back. But it comes after you've written that original check. Everybody should qualify for the federal tax credit of 30%. And that, as long as the Inflation Reduction Act stays in force, that's gonna be that way. Then we have the net system cost. The net system cost is this $25,000 minus these incentives. And a lot of times that net system cost is what's reported by the installer, or it can be. But we have to be careful because remember, we're writing the check for the full amount. But the net system costs are a reality. It just isn't right away. Because if I install this today in Nebraska or in any part of the United States, I can't get that federal tax credit until I do my taxes next year. So there's a little bit of a delay on that. This system cost has to get paid back by my production times the value of that electricity and pays back over time. And that's the payback. How many years does it take for the production times the value of the electricity I generated to pay back that net system cost? So some examples are, I ran these for a location around Lincoln, Nebraska. But if you can access net metering, which is a policy I'm going to cover in just a moment, the payback is 16 years for this particular example. I'm getting retail credit for essentially everything that it makes is being valued at retail rate. Net billing, I'm valuing some of my electricity at retail, but some of it at wholesale. And those are the most two common policies, and I'm going to cover those in a moment, that we see in Nebraska, because not all of Nebraska does everybody get net metering, because they're in the state law, there are some thresholds that have to be, that when met, the utility doesn't have to do net metering anymore. And we're seeing that in a number of utilities in Nebraska. Buy all, sell all was a policy that was used in a few places. It's less used today, but in this case, the payback on buy all, sell all policy isn't very good. And so that's one of the reasons talking to you today to say, what's the payback in my location? Well, I don't know. We need to do a little more work to figure that out, because it depends on if your utility uses net metering or if they use net billing, or maybe if they were to use buy all, sell all, it's quite variable. Also, the price of electricity across the state is somewhat variable, and that makes a difference as well. So it's much more unique calculation, and I'd be happy to work through that with you if you're interested. Let's talk about net metering. So we're going to draw some pictures here, and we're going to imagine that electricity is flowing from the grid. We're going to call that A. Electricity flows from the solar to the load. We're going to call that C. And then we have excess generation that might happen if the solar is generating more than the house at any given moment. And we're going to call that B. So in a net metering scenario, which is a state law, but again, with those thresholds, so most of Nebraska this still applies. At the end of a billing period, we need to calculate our bill. And you can imagine if A is bought from the utility, it's bought at retail rate. And let's just make retail rate, for the lack of a better number today, we're going to make it 10 cents just for a round number to have. So retail rate is worth 10 cents. So if that electricity is going to the house down here at C, that is electricity I did not have to buy from the grid. So we can imagine it's worth 10 cents because I did not have to buy it from the grid. Now we sent electricity to the grid, and they metered it, but then it got used by the neighbor. So you can almost think about that electricity I gave it to the grid, my neighbor bought it from the grid, even though it was my kilowatt hour. In a net metering situation, at the end of the billing period, we're just simply going to take A minus B. So if A was 500 and B was 400, A minus B equals 100. That means that this 400, because it was subtracted from A, was all worth 10 cents. And so as long as what I send to the grid is less than what I take from the grid, all of that electricity is worth retail rate from in my bill. And that's why net metering is such an economic positive for the consumer that is able to access that policy. Now, there are scenarios you might have a month, depending on the size of your system, where we'll call this 300 and we'll call this 350. So in this case, A minus B is equal to negative 50. So the utility owes me for 50 kilowatt hours, but they're not going to pay me the retail rate because I provided them just the energy portion. I didn't provide them the delivery of that kilowatt hour to the grid. I simply delivered them energy. So they're going to pay me a lower rate called a voided cost. And so in this case, that might be, let's call it 5 cents, 0.5. So they owe me, 25 cents in this case. And so they're going to pay that to me however they decide to do that. There's some different utilities do different things, but I get a credit back from them at a lower than retail rate per kilowatt hour. So now that's net metering. Now let's talk about net billing. So let's say you're in a utility that has met the threshold. They aren't doing net metering. We're going to have these same flows of energy because that doesn't change. In this case, though, at the end of the month, they're simply going to take A times the retail rate, 10 cents, and they're going to charge me for all of A at 10 cents. Then they're going to give me a credit, and they're going to pay me for all of B at, well, let's call it half of that. Clean that up a little bit, but at 5 cents. So the voided cost rate. And so in this case, that B isn't worth as much because remember in net metering, at least some of that B was worth 10 cents. Now all of the B is worth 5 cents. C is still worth 10 cents in the net billing because it's A that I didn't buy. I avoided buying that A, so that C is still worth 10 cents. So you can see net billing is not as advantageous to the consumer or solar consumer. And so that's where paybacks get a little bit longer in a net billing scenario. So it's important to understand which scenario or what policy you are going to be dealing with when it comes to the billing procedure. I've just laid these out. I'm going to kind of skip them, but I've just laid these out with in pictures. So if you ever do get my slide set, all my pictures that I drew are kind of here. So let's run through one. Oh, go ahead.
Oh, how much more of this do you have?
I'm getting close.
Gotcha. Okay. Because we needed to wrap up around 6-ish. Because
that's the plan.
Okay.
Very good.
Right now we will launch the Q&A, the poll. So if we could just have the attendees do those, that would be great. But John, sorry to interrupt, and go ahead, take it away.
Okay. Go ahead and work on that poll as we get done. I just have an example, and then I'm pretty much done here. But in this case, I have a gross system cost. I have a 5 kW solar array, which would be a reasonable size for a home. 250 a watt. Remember, that's just my example. When you get a bid, it's going to come in, probably between 250 and just over $3 is pretty common today. So I'd have a gross system cost of $12,500. I get a federal tax credit of $3,750, which I get back in my taxes after I do my taxes the next year. So I have a net system cost of $8,750. My production for my 5 kilowatt system is 7,100 kilowatt hours per year, approximately. And I'm going to value that at 8.1 cents per kilowatt hour based on my rate schedule. And I'm saving $575 per year. So my payback is 15.2 years. There's a number of things wrong with this cash flow example, but the reality is this simple cash flow example is a good back of the hand calculation that gets you in the ballpark. And if you don't like the what you came up with, that's going to tell you, well, maybe it's not, it's likely going to get a little worse probably. But the reality is, what's wrong with this really quick, because I have just a minute, but what's wrong with it is most utilities have a varying rate schedule, winter and summer, so that's not quite right. Another thing that happens is we don't quite produce the exact same every year, so that's not quite right. It's close. The other thing is we might have to fix it. So we have some operation and maintenance costs. We also might have some insurance costs depending on how that goes. And so another thing is that these solar panels do produce a little bit less over time. So we'd have that. And so when we bring in all of those factors in, and do it, and with the inflation value of money as well, the payback is 16 years. I know that's not a lot different, but when we do a good job, we can have a more accurate and we can feel better about the numbers that we came up with. So in this case, this particular cash flow example, 16 years is a more accurate number than the 15.2. So here's my kind of last slide, and then we'll go to as many questions as we can handle, as we have time for. But if you are going to interested in a solar array for your home or your farm or your business, one place to look for installers is at these different utilities websites. They have trade ally programs where installers work with them on some to do some training. So LES, OPPD, and MPPD, you don't have to be one of their customers to look at their trade ally list. Go ahead and look at their list. There are also some other utility or other developers out there, or installers. You want to get multiple quotes. You need to make sure that one isn't just trying to make as much money as possible on you or something like that. So get more than one quote. Ask lots of questions. Ask about experience. Ask to go see them. Ask what their philosophies are for sizing based on your goals. If they tell you, well, you need this system size, and they never asked you, what are you trying to accomplish? Wonder why they didn't ask. What are your goals? They need to want to build something that meets what you want and need. Ask questions about the equipment. They should be very open about what brands that they're selling. Not to say that there aren't lots of different brands, particularly of solar panels out there, that could work, but they need to be very open and honest about which ones they are so that you can look them up. And good ones will be open and honest. Ones that you just wonder why somebody won't tell you. So, now granted, they might have to say, well, this is what I can get today. In 6 months, I might have, or even in a month, I might have to get a different one, but they're open and honest about that as well as good. Okay. So there's lots of good brands out there, particularly of panels. There's less numbers of brands of inverters out there. So that's what I have. I'm going to answer as many questions. Here's my contact information. I'd be happy to visit with you on email or on the phone. Let's see what you got. When you did the labor yourself, how much did the cost come down? Half. The answer is fairly close to half. Is right. A lot of the cost of a system is in the labor. About 20% of the cost of a system is in the solar panel. About 10% of the cost is in the inverter. So I've just added 30% is all. And then all the balance of the system might get you close to 50%. And then the rest of it's going to be in labor and a few other little things in permitting. So I would say my number was pretty close to half. Now, again, I didn't count my labor. I could have thought about that in my calculation, but I installed it and I thought, okay, I'm just doing this in the evenings and the weekend. Would I have been doing something to make money that I can charge for my labor? No. So I decided that my system, when my cost benefit analysis was going to be based on not having a labor cost. My payback then came in at about 9 years. At the time, I installed it in 2017, and I'm in about 17, 17, 18, 19, 20. I'm pushing pretty close to that. I got another year or so to go, and I should have that thing paid off. But I also look at what were my goals. Since I haven't seen another question come in, I'm just going to answer what were my goals. I had a mixed goal of, yes, I wanted some green energy. Yes, I wanted to have a lower electric bill, but I also wanted to have a place to park my antique tractor. And so being able to put this solar up with a roof underneath allowed me to then have that benefit of being able to park my antique tractor. And now I've got my chickens overwinter under these and things like that. And I would tell you that I have a roof that pays itself off in 9 years. Not many people can say that, right? Because if I would have just put the roof up without the solar, then I have the savings of the value of my tractor, which I might have saved, $30 in the value of my tractor over 10 years because it didn't change that much. So what about hail is a good question. They are susceptible to hail, but they are tougher than your roof. And so you think about your asphalt shingle roof is going to be ruined way before the solar panels are going to get ruined. Really, the examples of broken solar panels in Nebraska in the last 15 years, the only solar panels I've seen break because of hail got hit with hail baseball size or larger. Everything else survived. And so they are very tough, but they're not impervious. The good news is that if you work it out and make sure that your insurance company knows it's there, they are covered under your homeowner's insurance policy, and they'll get fixed based on that. So that's the good news on that. So any last questions? We got to finish up by 6 o'clock. Thank you all for joining us.
We have a few more questions in the Q&A
yeah, go ahead.
section, which you can answer with the time we have left. These will be the last questions.
Yeah.
Okay. Can you see them?
Yeah, I just found them here.
Okay, perfect.
Can you use one microinverter for 2 or more panels? There are some companies that sell microinverters that work for 2 panels, but you want to only follow what the company does. So, and that's easy because if it only works for 1 panel, there's only 1 connection to it for the solar input. But one with double has 2 connections. So there are some microinverter companies that have 2 panels per 1 inverter. Most of them are 1-to-1. What would be an appreciation on your real estate if solar panels was already established as a new homeowner? Would you only benefit from the system? In general, what I've seen is that solar at a home, on a roof or on the ground, has a variable effect on the value of the home. So in some cases, it might have a little bit of a bump in the price of a selling price. In many cases, it doesn't have a bump because the average buyer doesn't necessarily maybe give value to it, but the right buyer does. Now, how does your appraiser think of that, or the county assessor? That's a little bit variable. The county assessor should be looking at other houses with solar to decide if that's a higher value. They may or may not do that. An insurance company, my insurance company, came out and they weren't worried about the solar, but they did say, if you are going to replace this in a catastrophic, let's say a fire or a tornado, do you want to replace it with solar? And if so, we need to increase the replacement value of your house. And so we increased that, and it cost me $20 a year to increase that on my insurance. So you have that kind of variability where it can have an effect, but isn't necessarily have a big effect. What is the best panel with regard to hailstorms? I don't know if I could name a panel that's better. I would say that they're all tested. I I think they're all tested to the same standard, which is like a golf ball at a certain speed. So they are all tested and they are all pretty tough. So I'm not sure I can name a panel that's better or worse. I would say they're all good, but again, that doesn't mean that they're impervious. So they're just very tough. So good questions.
All right, looks like we are all good on questions.
All
John, do
right.
you have anything that you just last you want to add?
Nope, just thanks for coming and feel free to contact me. My information's on the screen.
Awesome. All right. Thank you, John. I appreciate
Thank you,
your time.
John.
Thank you for filling out the survey if you did, and we will see you all in the next webinar.